In the last video, we discussed about the Michaelis-Menten kinetics and about the Lineweaver Burk plot. Now, the Lineweaver Burk plot is important because the tracings can help us distinguish between reversible competitive, reversible uncompetitive, and reversible non-competitive inhibitors. Again repeating, reversible inhibitors of enzymes or any particular reaction are three types: competitive, uncompetitive, and non-competitive. In a competitive reversible inhibitor, if a competitive reversible inhibitor is present in a reaction, what will happen? So this is the enzyme. Suppose these cups represent the enzymes and these black dots are substrates and I is the inhibitor. Now, we suppose have enzymes and we add substrate to it, so the substrate will attach to the enzyme binding sites and we have products. Now, if we have a competitive reversible inhibitor, it will go and bind to the same site to which the substrates attach. That is why they are competitive. They bind to the same sites on the enzyme on which the substrate attach. So what we can do is, if we increase the number of substrate molecules, in this particular scenario, we can see that there are 1, 2, 6, 12 substrate molecules and only 4 inhibitor molecules. So mathematically what happens, if we are increasing the amount of substrate molecules, the probability that the substrate will bind to the enzyme site will increase. So if the substrate is able to bind to all of the enzyme sites, when we increase the substrate concentration, even in the presence of a competitive reversible inhibitor, the Vmax is going to remain same because all of the sites are bound by substrates. Now, let us look at what happens to Km. So what is Km? Km is actually the substrate concentration at which half the Vmax is achieved. Now see, to keep the Vmax same, what did we have to do? We had to increase the substrate number. And as we have already discussed, if more amount of substrate is required to produce the same Vmax, then the Km is going to increase. That means the affinity of the substrate to enzyme has now reduced. So we are requiring more amount of substrate to produce the same Vmax. So ultimately what has happened? We have same Vmax but increased Km. Now if we plot this in a Michaelis-Menten, Lineweaver Burk equation, let us take a new whiteboard. If we are plotting it in a Lineweaver Burk plot, it will look like this. As we already discussed, the Vmax is same. So the 1 by Vmax is going to remain same. So our point of 1 by Vmax is same. Just as in the previous curve where there was, so this particular black line is when there is only the substrate and there is no inhibitor present. So if this is the Vmax, we have already discussed the Vmax is going to remain same. So even in the presence of the inhibitor, the Vmax will be this point. Now in the presence of the inhibitor, we discussed that Km is going to reduce. Now if the Km is going to reduce, what is going to happen to 1 by Km? It is going to increase. So the Km value in absence of the inhibitor was here. Now if 1 by Km is increasing, it will shift to somewhere here. So the new point is here. In the presence of competitive reversible inhibitor, the new 1 by Km is here. So if you draw a line between these points, we get a new Lineweaver Burk curve here. So this represents the change in the curve when we have a reversible competitive inhibitor. Now let us discuss the second type of reversible competitive inhibitor, which is uncompetitive inhibitor. Now the uncompetitive inhibitor, to understand this, just look at this particular slide. See, we have enzymes and we have substrates. So what will happen when we add substrates to this particular enzymes? They will cause the appearance of an allostric inhibitor site. Once we add the substrate to the enzyme, after that this allosteric inhibitor sites will appear on the enzymes. They were not present previously. They appear only after the substrate binds. So when you add the inhibitor now, this inhibitor will go and bind to the allosteric inhibitor sites. So what happens to Vmax and Km over here? Once the inhibitor binds to the enzyme substrate complex, the velocity of the reaction is going to reduce because it will inhibit the production of the product. So the Vmax is going to reduce. So once the Vmax reduces, 1 by Vmax is going to increase. Now this inhibitor, once it binds to these allosteric sites, it causes a strong bond between the substrate and the enzyme, and the substrate now cannot dissociate from the enzyme substrate inhibitor complex. It binds very tightly. The substrate cannot dissociate from the enzyme substrate inhibitor complex. So the substrate's affinity for the enzyme increases. So if the substrate's affinity for the enzyme increases, the Km will reduce. Now if the Km will reduce, 1 by Km is going to increase. Now if we plot this on a Lineweaver Burk curve, so this black line is when there are no inhibitors. In the presence of an uncompetitive reversible inhibitor, we said that the 1 by Vmax is going to increase. So our previous 1 by Vmax was here. If it is increasing, it will go somewhere here. And we also discussed that 1 by Km is going to increase. So 1 by Km was previously here when there was no inhibitor, and if it increases, it is going to go somewhere here. Now if we draw a line joining these two dots, we get a curve that shifts like this. The slope of the curve remains same. Why slope of the curve remains same? The slope of the curve is actually the ratio of Km to Vmax. We see that Km has also reduced and Vmax has also reduced. Hence the slope is going to remain same. But 1 by Vmax has this shifted up because Vmax has reduced, and 1 by Km has gone to the left because Km has reduced. So the slope shifted to the left like this. So this is how the curve will look if the enzyme to the enzyme substrate complex we add a inhibitor which is uncompetitive reversible in nature. Now coming to the last type of reversible inhibitor, that is the non-competitive inhibitor. Now in a non-competitive inhibitor, the scenario looks like this. We have an enzyme, and you can see that these enzymes already have an allosteric inhibitor site. They are not going to appear after the addition of substrate. These allosteric inhibitor sites are already present. Please try to understand this difference between uncompetitive and competitive here. In uncompetitive, the allosteric inhibitor sites, they appeared only after we added the substrate to the enzyme substrate complex. But in non-competitive reversible inhibitors, these inhibitor sites are already present on the enzymes. So suppose we are adding substrate to such enzymes and then we add inhibitors to this particular reaction. There can be two types of situations which arise. If the substrate is close to the enzyme, then the enzyme substrate complex can form and we can have the formation of product. But if the inhibitor is close, then the inhibitors will bind to the enzyme substrate complex and no product is produced. Now if no product is produced, then it is very logical that Vmax is going to reduce. Now if Vmax is going to reduce, 1 by Vmax is definitely going to increase. Now what happens to Km? You see, the allosteric inhibitor sites were already present. So the substrate is going to bind to enzyme sites with the same affinity because the allosteric sites were already present. There is no conformational change here. Substrate is going to bind to the enzyme with same affinity. So Km is going to remain same. So if Km remains same, 1 by Km is going to remain same also. So if we draw a Lineweaver Burk curve over here, it will look like this. As we discussed, 1 by Vmax is reducing, so Vmax is reducing, so 1 by Vmax will increase. So if this is the curve where there was no inhibitor, and this is the Vmax over 1 by Vmax over here, and we are saying that the new 1 by Vmax has increased, so it will be somewhere here. Now we already discussed that Km is going to remain same, so the Km is here in absence of the substrate inhibitor, and in presence of the inhibitor also Km is going to remain same, so 1 by Km is going to remain same. So in these two new points we are getting, if we draw a line between these 2 points, we get a curve like this. So this is the curve that we will get when we add a non-competitive reversible inhibitor to an enzyme substrate complex. Hope this cleared the reversible inhibitors and Lineweaver Burk plot for you. If you revisit these videos thrice, then I'm sure you will get a clearer understanding of these very complex concepts. Thank you.